Pulsar Fusion, a UK startup founded in 2019, plans to build nuclear-powered reusable space tugs that could open up the solar system. In the more immediate future, the company is working on electric propulsion systems for use in low Earth orbit. As the orbital economy grows, mobility is a core issue that needs to be solved. Electric propulsion is used for placing satellites into operational orbits, end-of-life services, debris removal missions, and more. In this video, I'll first cover their near-term plans and then spend the rest of the video on Pulsar's more ambitious nuclear-powered deep space tugs. Operational fusion drives would be highly beneficial for a range of missions, such as cargo missions to Mars and deep space robotic missions to the outer planets. At the end of the video, I'll give my thoughts on Pulsar Fusion's ambitions. I'd like to hear your comments on the company, so please drop your thoughts and opinions in the comments section after watching the video. As always, I host a live weekend stream discussing all the space news while reading out viewers' comments and chat messages. The link is in the pinned comment. Okay, let's briefly go over their near-term plans for electric propulsion systems. Electric propulsion. In the coming years, thousands of satellites will launch to low Earth orbit for internet, communications, and AI computing. SpaceX's Starlink constellation, for example, numbers over 7,000 satellites in orbit, with many more constellations to follow. Pulsar offers 3 different power levels for their electric propulsion systems: LEO Bear at 500 watts, Moon Ranger at 5 kilowatts, and their top-of-the-range Mars Ranger at 10 kilowatts. The company has received grants from the UK Space Agency for work on their electric propulsion and nuclear technologies. The European Space Agency also gave them a €500,000 contract to advance work on Hall effect thrusters to make them ready for flight testing. Expect to see Pulsar Fusion engines in low Earth orbit in the future. Now, let's turn our attention to the far more radical and ambitious plans for nuclear-powered propulsion around the solar system. Pulsar Fusion's nuclear plans. Pulsar Fusion states on their website that their fusion drive redefines what's possible in space travel. Their Sunbird reusable space tug uses a 2 megawatt nuclear-powered fusion drive with a fuel efficiency of 10,000 to 15,000 seconds. To put this number into perspective, that level of fuel efficiency means the exhaust velocity would be between 98 to 147 kilometers per second. A fusion reaction produces 10 million times more energy per unit mass than a chemical rocket. Given the massive energy density in nuclear fuels, only grams are needed to propel 1 metric ton of payload to Mars in under 6 months. A Pulsar Sunbird tug could deliver 1,000 kilos to Pluto in 4 years, needing perhaps only 100 grams of deuterium and helium-3. This is possible because of the extremely high fuel efficiency and the energy density of the fuel. According to the Princeton Direct Fusion Drive, which is an academic study similar in concept to Pulsar Fusion, even ambitious outer-planet missions only require a few kilograms of fuel at most. That's without optimizing the trajectories. A fusion drive opens up the outer solar system, which is challenging to explore using traditional engines. The low fuel efficiency of chemical thrusters means gravity assists are needed for outer-planet missions, sometimes multiple assists per mission, making journey times extremely long. In addition, planetary alignment is necessary, which for the outer planets doesn't happen very often. Let's be clear, a Sunbird space tug produces very low thrust, so its main use is for cargo and supply missions to support human outposts, or for deep space robotic missions. For fast transit crewed missions, nuclear thermal propulsion remains the better option due to its high thrust. Sunbird's engine, dual direct fusion drive. Pulsar describes their engine technology as a compact design nuclear fusion engine to provide thrust and electrical power for spacecraft. The engine produces 2 megawatts of electrical power once it arrives in orbit, which can be used to power advanced payloads or equipment. The engine is a steady-state fusion propulsion system based on a set of compact linear fusion reactors. The company is currently working on an initial test unit. This prototype is intended for pre-fusion testing to validate the core hardware and subsystems. Fusion plasma is used to directly produce thrust, hence the name direct fusion drive. This differs from other nuclear propulsion concepts, such as nuclear electric propulsion, which first converts fusion energy into electricity to power a separate electric propulsion system. Pulsar plans to conduct an on-orbit test in 2027 to qualify their systems. This will include plasma generation, confinement, magnetic nozzle performance, exhaust velocity, power systems, and overall engine integration. The goal is to prove that these systems can operate successfully in the space environment. For their on-orbit test, Pulsar will likely use krypton as their propellant, just as they did during their first plasma test in March 2026. The first plasma milestone in March 2026. There is a lot of marketing buzz around the company, which can sometimes make it difficult to understand what has actually been achieved. For instance, let's examine the first plasma milestone that occurred live at Amazon Mars conference hosted by Jeff Bezos. Pulsar showcased a confined plasma event using krypton gas in a prototype Sunbird exhaust test system. Electric and magnetic fields were used to guide and accelerate the plasma through the exhaust channel, generating thrust. Some of the headlines around the test were exaggerated. For example, claims such as world's first and exceptional moment created a misleading impression. The reality is that no nuclear fusion occurred during the test. There was no energy gain. It was just an ordinary plasma source and magnetic nozzle test, the kind of experiment that university labs conduct all the time. I'm not saying the test wasn't important. It did validate some of the hardware, but the marketing and hyperbole associated with it was over the top. Physics and engineering challenges. Before fusion drives can be built, some challenging physics and engineering problems need to be solved. The ignition temperature for the fuel in a Pulsar fusion drive needs to reach over 300 million degrees Celsius. In addition, the fuel's density must be maintained and the plasma confined. The reactor chamber must then be tested to ensure it can withstand the enormous temperatures and neutron damage caused by the fusion reactions. Even though the main reaction doesn't produce neutrons, some of the side reactions do. No one has built a working compact fusion drive yet, so Pulsar Fusion has to figure out the technology on their own. Okay, now let's turn to their fuel choice, which is one of the biggest risks for Pulsar: helium-3. Pulsar Fusion plans to use helium-3 as their fuel. Specifically, they intend to use a mix of deuterium and helium-3, an incredibly rare and expensive isotope of helium. This special type of helium, which is very difficult to produce, is essential for Pulsar's fusion drive. This is because helium-3 produces almost no neutrons when fusion occurs, unlike many other nuclear fusion fuels. As a result, only light shielding of the reactor chamber is needed. For spacecraft, every extra kilogram of mass on board requires more fuel to move it. Fusion drives therefore need to burn cleanly to avoid damaging the reaction chamber and reducing the lifetime of the spacecraft. Helium-3 costs $20 million per kilo and is very difficult to acquire, even if you can afford the price. This is because the quantum computing industry also needs this resource, and they've signed long-term supply contracts with suppliers already. Breeding helium-3. Pulsar is hoping that fusion startups will breed helium-3 in their reactors and sell this resource for profit. Unfortunately, it makes more sense for fusion startups like Helion Energy to use this ideal fusion fuel in their own reactors. Helium-3 produces more energy and generates very few neutrons. This extends the lifetime of the reactor, reduces maintenance costs, and increases profits through higher energy output. Helion Energy has already produced small amounts of helium-3 using their nuclear fusion reactor. This means the company can generate its own nuclear fuel with, as the company says, no space travel required. Lunar helium-3 mining. While Earth has very little helium-3, it's estimated that the Moon has over 1 million tons on its surface. I've covered Interloon extensively on this channel already, the most likely startup to extract helium-3 from lunar soil and return it to Earth for sale. Unfortunately, multiple companies specializing in dilution refrigerators for quantum computers have already signed deals with Interloon. Bluefuzz, for example, has signed a deal for 10,000 liters of helium-3 from Interloon annually, 2028 to 2037. So even if Interloon begins selling helium-3 commercially, there is no guarantee Pulsar Fusion can purchase any, especially if the quantity available is less than 10,000 liters per year. Realistically, Lunar helium-3 will not be commercially available before the 2030s. This isn't an immediate problem for Pulsar Fusion, since their fusion drive components and systems will take many years to design, build, and test. It's worth noting that a small payload demonstration mission to Mars to prove the Sunbird drive works would only require a small amount of helium-3. 10 grams is enough, considering the very high fuel efficiency of the drive. Why Pulsar Fusion has to use deuterium and helium-3 for its fuel? Why not use a dirtier nuclear fuel mix, say deuterium-tritium for the reactor? It would certainly be cheaper, but it comes with major downsides, one of which is, in my view, fatal for spacecraft. Many of the fusion startups are using deuterium-tritium fuel for their reactors to begin with, even if they eventually plan to use deuterium and helium-3. Pulsar has consistently stated that their baseline fuel for their Sunbird dual direct fusion drive is deuterium and helium-3. The reason Pulsar is so insistent on using this cleaner fuel is that almost no neutrons are produced. This dramatically reduces the amount of shielding required, which is critical for spacecraft. Using a dirtier fuel like deuterium-tritium would increase shielding mass by a factor of 50. Even for a small reactor chamber with a surface area of 10 to 20 square meters, the spacecraft would need 5 to 10 tons of shielding if it were using deuterium and tritium. This makes the spacecraft heavy, reduces the amount of energy produced, and shortens the life of the vehicle due to heavy neutron radiation damaging the reactor chamber. Another advantage of helium-3 is that it produces more charged particles, which can be accelerated using the magnetic nozzle to produce extra thrust. Neutrons have no charge and cannot be controlled by a magnetic field. In short, Pulsar's dual direct drive design is optimized for charged particles and does not work well with deuterium-tritium fuel. The bottom line is that nuclear fusion drives for spacecraft must use low neutron fuels to be viable. Alternative clean fuels. One other fuel comes to mind, so let's look at that before ending the discussion on nuclear fuel choice. This fuel is called proton-boron-11 or PB11. Like deuterium helium-3, it doesn't produce neutrons during fusion. In fact, this fuel produces even fewer neutrons inside reactions, so it requires almost no shielding. In addition, boron is available and cheap, so sourcing the fuel is no problem. No space travel required. Unfortunately, it has some downsides. The physics of igniting the fuel are more challenging because the ignition temperature is much higher. In addition, it produces less than half the energy of helium-3 fuel per reaction. So while this fuel has potential, the physics are difficult, making it technically challenging to produce an operational fusion drive using this fuel. That said, PB11 could potentially serve as a plan B for Pulsar Fusion if helium-3 sourcing becomes a problem, since this fuel would work well in the reactor chamber the company is designing. In the near term, however, deuterium helium-3 seems the most practical fuel to use. Final thoughts. It's great to see a company working on a nuclear fusion drive for space. An operational fusion drive would open up the solar system to robotic missions, although deep space crewed missions will likely need to wait until nuclear thermal propulsion becomes available. What do you think of Pulsar Fusion's dual direct fusion drive technology? Do you think relying on helium-3 to power their fusion drive is risky? Leave your thoughts and opinions in the comment section below. Thanks for watching. If you enjoyed this space video, consider buying me a coffee to help fund more episodes like this. The link is in the description. Watch the weekly live stream to see the images, clips and slides from this week's videos. It's a live Q&A on this week's space topics where I read out some of the best comments. The more people join, the more fun the live stream is. Be sure to like and subscribe so you'll see our upcoming videos. We make videos every week covering the space industry with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.